On June 6, 1944, Allied forces stormed the beaches of Normandy. But D-Day was only the beginning of the invasion, not the end. The massive army landing in France needed constant supplies: ammunition, food, fuel, vehicles, and reinforcements. Without these supplies, the invasion would fail within days. But there was a critical problem. The nearest major port was heavily defended by the Germans and could not be captured quickly. The solution was one of the most audacious engineering projects in history: to build entire artificial harbors in England, then tow them across the English Channel and assemble them on the French coast. This is the story of the Mulberry Harbors. In 1942, Allied planners began seriously considering an invasion of France. They quickly identified a fundamental challenge. Any invasion required capturing a major port intact. Without port facilities, supplying a large army would be impossible. Ships could not unload directly onto beaches in sufficient quantities. The Germans understood this perfectly. They heavily fortified every port along the French coast. Concrete bunkers, artillery, minefields, and elite troops defended places like Cherbourg and Calais. Even if the Allies captured a port, the Germans planned to destroy it. Demolition charges would wreck the docks, cranes, and facilities. Sunken ships would block the harbor entrances. Repairing a sabotaged port could take months. The invasion force would starve long before then. Historical precedent supported these fears. In 1942, the British and Canadian raid on Dieppe had been a disaster. Attempting to seize a defended port resulted in catastrophic casualties. The raid proved that frontal assault on ports was suicidal. Yet without ports, invasion seemed impossible. It was a military catch-22 that threatened to make the liberation of Europe unachievable. Winston Churchill, Britain's Prime Minister, refused to accept this. In May 1942, he wrote a now famous memo. It stated simply, "They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves." Churchill was proposing something radical. If the Allies couldn't capture a port, they would build their own and bring it with them. The idea of portable harbors was not entirely new. During World War I, engineers had experimented with floating piers, but nothing on the scale now being contemplated. A committee was established under Brigadier Bruce White to investigate the feasibility of artificial harbors. The requirements were daunting. The artificial harbor had to accommodate large ships, including Liberty ships that carried most supplies. It needed to handle the extreme tidal range of the Normandy coast, which could exceed 20 feet between high and low tide. The harbor must protect ships from storms and waves. The English Channel was notoriously rough. It had to be transportable across 100 miles of open ocean and assembled quickly under potentially hostile conditions. Finally, it needed sufficient capacity to land thousands of tons of supplies daily. The engineers divided the problem into components. First, they needed breakwaters to create calm water. Second, they required floating piers that could rise and fall with tides. Third, roadways had to connect piers to the shore. Fourth, the entire structure needed anchoring systems. Each component presented unique engineering challenges. Multiple design teams worked on different approaches. The best ideas would be combined into the final design. By late 1942, the basic concept was approved. 2 complete artificial harbors would be built. One for American forces, one for British and Canadian forces. The project was given the codename Mulberry, after the mulberry tree for no particular reason, except to maintain secrecy through meaningless terminology. What followed would be one of the greatest engineering achievements of World War II. Creating calm water in the rough English Channel required massive breakwaters. Traditional breakwaters were permanent stone structures. Built over years, these were impossible given the time and circumstances. Engineers developed 3 different breakwater systems. The first was called corncob. These were old ships that would be deliberately sunk to form a barrier against waves. Over 70 obsolete merchant ships and warships were gathered. Stripped of useful equipment and prepared for scuttling, they would be towed to Normandy and sunk in a line, creating the outer breakwater. The second system was called Phoenix. These were massive concrete caissons, essentially huge concrete boxes. Phoenix caissons came in various sizes. The largest were 200 feet long, 60 feet wide, and 60 feet tall. Each weighed over 6,000 tons. They were built in dry docks all around Britain. When complete, the docks would be flooded, and the caissons would float out to be towed to assembly points. In Normandy, They would be positioned and flooded, sinking to the seabed to form a breakwater wall. The third system was called bombardone. These were floating steel cruciform structures, anchored in deep water to break wave action before waves reached the Phoenix caissons. Together, these three systems would create over 5 miles of breakwater, protecting an area of water equivalent to Dover Harbor. Building the Phoenix caissons alone required 330,000 cubic yards of concrete and 31,000 tons of steel reinforcement. This was equivalent to building a large city, all while Britain was already stretched thin by the demands of war production. The floating pier system was perhaps the most innovative component. Called whale, these piers had to accommodate extreme tidal movement, while remaining stable enough for vehicles and cargo. The design used floating steel pontoons. Each pontoon was essentially a hollow steel box. Multiple pontoons were connected to form a floating roadway. The pontoons were held in position by steel legs, called spuds, that were driven into the seabed. The pontoons could slide up and down these spuds, rising and falling with the tide. Flexible connection points allowed the pier sections to move independently with wave action, while maintaining structural integrity. Each harbor would have multiple piers, allowing several ships to unload simultaneously. The piers extended from the beach out to deep water. Some were over half a mile long. At the seaward end, pierheads provided mooring for large ships. These pierheads were essentially floating platforms, equipped with bollards and fenders. Ships would tie up alongside the pierheads and unload cargo onto the floating roadway. Vehicles could then drive along the pier to shore. The connection between floating pier and beach required special flexible bridge sections. These had to accommodate the tidal movement while allowing continuous vehicle traffic. Engineers designed hinged ramps that could adjust to different water levels. The entire whale system was designed for rapid assembly. Sections would be towed across the channel and connected on site in a matter of days. Building the Mulberry Harbors required an industrial effort of staggering scale. Over 20,000 workers were employed on the project. Construction took place at sites all over Britain, from Scotland to the south coast. Phoenix caissons were built in dry docks, many of which had to be specially constructed or modified. Concrete production for the caissons required 150 concrete mixing plants operating continuously. The concrete had to be specially formulated to withstand seawater and extreme forces. Steel reinforcement bars were laid in complex patterns to give the caissons maximum strength. Building a single large Phoenix caisson took several months of intensive work. The whale pontoons were fabricated in shipyards, using standard shipbuilding techniques, but adapted for the specific requirements. Each pontoon had to be watertight and precisely balanced. Quality control was critical. A single leak could sink an entire pier section. The spud legs were manufactured from steel tubes, up to 90 feet long for the deepest water sections. These had to be perfectly straight and immensely strong. Material shortages complicated everything. Britain was building ships, aircraft, and weapons, while simultaneously constructing the Mulberry components. Steel and concrete had to be allocated carefully. Priorities constantly shifted as military needs changed. Labor was also scarce. Many skilled workers had been conscripted into the military. Women, older workers, and even German prisoners of war were employed on construction. Security was a constant concern. The Germans could not learn about the artificial harbors, or they might prepare specific countermeasures. Workers were told they were building components for various unspecified purposes. The true nature of the project was known only to a few. Before committing to full production, the Mulberry components needed testing. Scale models were built and tested in wave tanks. Engineers studied how the structures responded to different wave patterns. Full-scale prototypes of key components were constructed and tested in actual sea conditions. On the coast of Scotland, experimental pier sections were subjected to storms and high tides. Early tests revealed numerous problems. Pontoons proved insufficiently buoyant when loaded with vehicles. The design was modified to add more flotation. Connection points between sections were too weak. They were breaking apart in rough seas. Stronger linkages were designed and tested. The spud legs tended to sink into soft seabeds. Special base plates were added to distribute the weight. Phoenix caissons experienced concrete cracking during towing due to wave stresses. Reinforcement patterns were adjusted. Each problem was solved through engineering iteration. Test, analyze, modify, test again. The process was time-consuming but essential. Failure in Normandy was not an option. The Mulberry Harbors had to work perfectly, from the moment they were installed. There would be no opportunity for repairs. While under potential enemy fire, by early 1944 the designs were finalized. Production shifted into high gear. With D-Day approaching, time was running out. In the weeks before D-Day, Mulberry components began their journey. Phoenix caissons were towed from construction sites to assembly points. This was a delicate operation. The caissons floated with only a few feet of freeboard. Rough seas could flood and sink them. Tugboats towed them slowly and carefully, sometimes taking days to cover short distances. The caissons were assembled in sheltered anchorages along Britain's southern coast. Hundreds of these massive concrete structures floated in lines awaiting D-Day. The old ships designated for scuttling were gathered and prepared. Crews would sail them across the channel, then deliberately sink them in position. It was a one-way voyage for these vessels. Whale components were loaded onto transport ships or prepared for towing. The logistics were staggering. Over 400 separate tows would be required, coordinating all this movement, while keeping it secret from German reconnaissance, was a triumph of military planning. German intelligence did detect unusual activity, but they didn't understand what they were seeing. The concrete structures were assumed to be some kind of coastal defense or storage facility. The Germans never imagined that entire harbors were about to cross the sea. On June 6, 1944, the invasion of Normandy began. As troops stormed the beaches under heavy fire, the Mulberry Harbors began their own invasion. The first components to cross were the corncob ships. On D-Day itself, old vessels were sailed across the channel under their own power. Despite German coastal guns and air attacks, by D-Day +1, the first ships were being scuttled. Explosive charges blew holes in their hulls. The ships settled onto the seabed, creating the first primitive breakwater. This gave immediate shelter for supply vessels. The Phoenix caissons began crossing on D-Day +2. Tugboats towed them in convoys across the channel. The crossing took 12 to 18 hours in good weather. Longer when seas were rough. Naval vessels provided escort and protection. German submarines still operated in the channel, and aircraft occasionally attacked convoys. Several Phoenix caissons were damaged during the crossing. Some sank before reaching France, but most arrived safely. Once in position, the caissons were flooded. Water was pumped into compartments, causing them to sink slowly to the bottom. Positioning had to be precise. Survey teams worked from small boats, directing tugboats to place each caisson exactly. Once settled, the caissons formed a solid wall, creating protected harbor space behind them. The whale piers came next. Pontoon sections were towed across and connected. Spud legs were hammered into the seabed, using pile drivers mounted on barges. The work continued around the clock. Engineers and construction workers labored, under threat of German artillery fire. By D-Day +12, the American Mulberry at Omaha Beach was partially operational. Ships were already unloading at the first completed piers. The British Mulberry at Gold Beach was progressing on a similar schedule. The artificial harbors were working. Supplies flowed ashore in increasing quantities. The gamble was paying off. On June 19, 1944, disaster struck. A severe storm, the worst in 40 years, hit the Normandy coast. For 3 days, gale-force winds and massive waves battered the artificial harbors. The American Mulberry at Omaha Beach took the full force of the storm. Bombardon floating breakwaters were torn from their anchors. They crashed into the Phoenix caissons, causing extensive damage. Whale piers were ripped apart by the waves. Pontoons broke free and were driven ashore. Spud legs bent or snapped under the force. Ships sheltering in the harbor were damaged. Some were driven onto the beach and wrecked by the time the storm ended. The American Mulberry was destroyed beyond repair. Weeks of work and enormous investment had been wiped out in 3 days. The British Mulberry at Gold Beach fared somewhat better. Its more sheltered location and stronger construction allowed it to survive with moderate damage. Repair crews immediately went to work, salvaging components and making emergency repairs. The storm was a crisis for the invasion. Supply delivery had been stopped for 3 days. Units at the front were running short of ammunition. The loss of the American Mulberry was a severe setback. Some Allied commanders feared the invasion might have to be suspended, but the engineers refused to give up. Usable components from the American harbor were salvaged and moved to reinforce the British harbor. Beach landing operations were intensified. using specialized landing craft to bring supplies directly ashore. Within a week, the supply situation stabilized. The invasion continued despite the setback. Chapter 10. Mulberry B continues. The British Mulberry, designated Mulberry B, became the focus of all harbor operations after the storm. Repairs and improvements continued throughout the summer. The harbor eventually had 6 piers in operation, each capable of handling large cargo vessels. At peak efficiency, Mulberry B could handle 7,000 tons of supplies and 1,500 vehicles daily. This was equivalent to a major commercial port. The harbor operated 24 hours a day. Floodlights illuminated nighttime operations. Ships queued offshore waiting their turn to unload. Vehicles drove continuously along the piers, from ships to shore and onto inland roads. The tidal range in Normandy was extreme, but the floating pier system handled it perfectly. Piers rose and fell with the tide, while maintaining continuous operations. Maintenance crews worked constantly, repairing storm damage and normal wear. The harsh marine environment was tough on equipment. Saltwater corroded metal components. Concrete surfaces showed stress fractures. But the harbor kept functioning. By late August, the port of Cherbourg was captured and gradually brought back into operation. This reduced pressure on the Mulberry Harbor, but Mulberry B continued operating. Until November 1944, it had served for 5 months, far longer than originally planned. During its operational life, Mulberry B handled over 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. Without it, the Normandy campaign would have been far more difficult, perhaps impossible. The Mulberry Harbors taught valuable engineering lessons. First, massive projects could be completed on impossibly tight timelines when necessary. The entire project from concept to deployment took less than 2 years. Second, modular construction allowed distributed manufacturing and rapid assembly. Components built all over Britain could be brought together and integrated successfully. Third, redundancy and robustness were essential. The storm destroyed the American harbor, but the British harbor survived because it had stronger construction and better siting. Fourth, testing under realistic conditions was crucial to identifying weaknesses. Problems discovered during Scottish tests were fixed before deployment. Fifth, nature always has the final word. Even the most sophisticated engineering must respect environmental forces. The storm was more powerful than anticipated, and the American Mulberry paid the price. Sixth, flexibility in response to failure can salvage success from disaster. When the American harbor was destroyed, engineers adapted and continued operations. Finally, sometimes audacious solutions are the only solutions. The idea of towing harbors across the sea seemed absurd to many, but it proved both possible and effective. The Mulberry Harbors had profound impact on the war's outcome. Most fundamentally, they made the Normandy invasion possible. Without artificial harbors, the Allies would have needed to capture a major port immediately. This would have forced them to land at heavily defended locations, like Calais or Le Havre. Casualties would have been catastrophic. The invasion might have failed entirely. Instead, the Mulberries allowed landing on relatively lightly defended beaches. This strategic surprise was decisive. The harbors also provided sustained logistics. During the critical first months, Allied armies could build up strength before breaking out from the beachhead. Without the Mulberries, supply would have been limited to what could be brought ashore on landing craft. This was insufficient for offensive operations. The Germans recognized the harbor's importance. They attempted several attacks on the installations, using frogmen, explosive boats, and artillery. But these attacks were largely unsuccessful. The Mulberries proved difficult to damage significantly. Their sheer size and distributed structure made them resistant to attack. The psychological impact was also significant. German commanders were shocked that the Allies could create harbors from nothing. This demonstrated Allied industrial and engineering superiority in a way that was impossible to ignore. Military historians generally agree that the Mulberry Harbors shortened the war. By enabling rapid buildup in Normandy, the invasion succeeded months earlier than would otherwise have been possible. Behind the technical achievement were thousands of dedicated individuals. Brigadier Bruce White led the overall project, coordinating between military planners and civilian engineers. His leadership kept the project on schedule. Despite countless obstacles, Alan Beckett designed the floating pier system. His whale piers were engineering marvels. combining simplicity with effectiveness. Guy Monsell designed the Phoenix caissons, creating structures that could be built quickly, yet withstand extreme forces. The 20,000 workers who built the components often worked in dangerous conditions. Construction accidents claimed several lives. The workers knew their efforts were vital to defeating Nazi Germany. The tugboat crews who towed components across the channel faced submarine and air attack. Several tugs were sunk during the operation. The assembly crews in Normandy worked under threat of German artillery. They continued despite casualties, knowing that every hour of delay meant Allied soldiers went without supplies. The maintenance personnel who kept Mulberry B operating for 5 months after the storm performed miracles of improvisation, repairing equipment with limited resources. All these individuals contributed to one of engineering's greatest triumphs. Most remained anonymous, but their collective achievement helped win World War II. After Mulberry B ceased operations in November 1944, the harbor was partially dismantled. Some components were salvaged for other uses, but much of the structure was simply abandoned. The Phoenix caissons were too large to move economically. They remain on the seabed to this day, visible at low tide off the Normandy coast. These concrete giants have become artificial reefs, colonized by marine life over decades. Some caissons have been designated historical monuments, protected from removal or alteration. Divers explore the structures, marveling at the engineering and the history they represent. The scuttled corncob ships have mostly disintegrated over time, but some wrecks remain visible, rusting reminders of their final voyage. The whale components were mostly scrapped. The steel was valuable for post-war reconstruction. A few sections were preserved in museums, including pieces at the D-Day Museum in Portsmouth and the Arromanches Museum in Normandy. The technology developed for Mulberry influenced post-war harbor engineering. Floating pier systems became common for temporary ports and offshore installations. The lessons in rapid construction were applied to peacetime infrastructure projects. Today, the remains of Mulberry Harbor attract thousands of visitors annually. People come to see the physical evidence of one of history's boldest engineering projects. The Mulberry Harbors left lasting lessons about engineering and warfare. First, logistics win wars as surely as battles. The Mulberries enabled sustained operations that tactical brilliance alone could not achieve. Second, apparently impossible challenges can be solved with innovative thinking. The idea of portable harbors seemed absurd, until engineers proved it could work. Third, large-scale projects require coordination between many disciplines. Military planners, civil engineers, naval architects all contributed essential expertise. Fourth, secrecy can be maintained, even in massive industrial efforts. The Germans never understood what was being built until the harbors appeared in Normandy. Fifth, engineering must account for worst-case environmental scenarios. The June storm was beyond design parameters, but should have been considered possible. Finally, the Mulberry Harbors demonstrated that civilian engineering skills are crucial military assets. The project succeeded because Britain's best engineers were mobilized to solve a military problem. Conclusion: Harbors of Hope. The Mulberry Harbors stand as monuments to human ingenuity and determination. In the desperate struggle against Nazi tyranny, British engineers accomplished what seemed impossible. They built harbors that could be transported across the sea and assembled under fire on enemy shores. The scale of the achievement was staggering. Over 500,000 tons of concrete and steel, shaped into components that worked together as a functional harbor system. The project employed cutting-edge engineering, combined with brute industrial force. Innovation met with determination to create something entirely new. The Mulberries proved that the seemingly impossible could become reality when necessity demanded it. Churchill's simple memo had sparked one of the war's most ambitious projects. Though the American harbor was destroyed by the storm, the British Mulberry more than justified the entire effort. It handled millions of tons of supplies during the critical months after D-Day. Without these supplies, the Allied armies could not have broken out of Normandy. The liberation of Europe would have stalled. The war would have lasted longer and cost many more lives. Today, visitors to Normandy can still see the Phoenix caissons at Arromanches. These concrete monoliths covered in barnacles and seaweed are physical reminders of an extraordinary achievement. They stand as testament to the engineers who refused to accept that something was impossible. and to the workers who built the impossible. In factories, dry docks, and shipyards across Britain, the story of the Mulberry Harbors is ultimately about solving problems when the stakes could not be higher, about human creativity applied to the most urgent of needs, about the power of engineering to change the course of history. The harbors that crossed the sea did more than just deliver supplies. They delivered hope to a continent under Nazi occupation. They proved that the Allies had the industrial might and technical skill to overcome any obstacle. The Mulberry Harbors were engineering marvels that helped win a war, artificial harbors that enabled the greatest amphibious invasion in history, concrete and steel structures that became instruments of liberation and monuments to the indomitable human spirit.